Manuel Rocha. For me, it's a great pleasure to give the welcome in this 38th lesson, Professor Manuel Rocha. Professor Manuel Rocha is for Gulbenkian a reference, and for Portugal and the Portuguese science. That's why I am here saying that for us is a great pleasure and honor to have the lessons, because these lessons are remarkable. That's why I only give you the welcome, and I thank very much all this cooperation in memory of a great reference of our culture and our science. That's why I give not only the welcome, but many thanks, and congratulations because of the permanence, because if we persist, that's an element absolutely fundamental concerning the memory of Professor Manuel Rocha. Professor Manuel Rocha was a reference in science, but also in citizenship. He was a great citizen and a reference, and we are very pleased to welcome this initiative. Thank you very much. Congratulations, and well, thank you.
Então, muito boa tarde a todos. Começo por agradecer à Fundação Calouste Gulbenkian, aqui representada pelo Dr. Guilherme Oliveira Martins, na qualidade de administrador, por nos receber uma vez mais nesta sua casa para este evento tão querido da comunidade geotécnica. Portanto, devo destacar o apoio que temos tido da Fundação Calouste Gulbenkian ao longo destes anos, na forma carinhosa como tem acolhido este evento e nas facilidades que tem dado, quer à Associação de Geotécnicos Antigos Alunos da Universidade Nova, quer à Sociedade Portuguesa de Geotecnia, para podermos continuadamente acolher este evento nestas condições. Mesmo o ano passado, como sabem, em condições difíceis, mesmo assim foi possível realizar aqui na Fundação Calouste Gulbenkian este evento, esta lição Manuel Rocha. Portanto, fazendo este introito, que não podia deixar de ser, começo em nome da Associação de Geotécnicos Antigos Alunos da Universidade Nova, representado aqui pela engenheira Quintela, sua presidente, e em nome da Sociedade Portuguesa de Geotecnia, desejar a todos que sejam muito bem-vindos a esta 38ª lição Manuel Rocha, não é? Um evento singular para a comunidade técnica e científica portuguesa, muito particularmente para a comunidade geotécnica. Ainda um especial agradecimento à família do engenheiro Manuel Rocha, que sempre nos honra com a sua presença e que hoje está aqui representada pela sua filha, doutora Teresa Rocha Félix, e esposo, Dr. José António Félix Filho, e ainda pelo seu filho, Dr. Manuel Rocha. Muito obrigado pela vossa constante presença neste evento. Queria também dar um cumprimento especial ao professor Ricardo Oliveira, que terá a amabilidade de proceder à apresentação do nosso palestrante, que está aqui do lado esquerdo, do meu lado esquerdo da mesa, e ainda à professora Isabel Fernandes, que está à minha esquerda, que no final fará os votos de agradecimento desta lição. Ainda um cumprimento muito especial ao Sr. Vice-Presidente do Laboratório Nacional de Engenharia Civil, o Engenheiro Eduardo Fortunato, que também nos honrou com a sua presença, e também ao Sr. Bastonário da Ordem dos Engenheiros, o Engenheiro Carlos Mineiro Ares, que por motivos de última hora não pôde estar presente neste evento. Passaria, sem mais demoras, então, a convidar o professor Ricardo Oliveira a proceder à apresentação do professor Scott Burns, o nosso ilustre palestrante de hoje. Muito obrigado.
Boa tarde a todos. desejo que apreciem bem a palestra que vão ouvir e cabe-me a mim fazer uma apresentação do nosso Dr. Scott Burns, de uma forma fácil para mim, por muitas razões, mas que desde há 20 anos nos encontramos pelo menos uma vez por ano e continuamente fazendo amizade, bebendo um vinho do Porto em conjunto, etc. Eu começo por uma saudação a todos os membros da mesa, nomeadamente ao Dr. Guilherme Oliveira Martins, que não está na mesa porque, por razões estratégicas, preferiu ficar naquele lugar, e referir que a Fundação Calouste Gulbenkian, como foi já referido há pouco por ele próprio, sempre disponibilizou este auditório para o efeito desde 1984. A primeira lição Manuel Rocha foi feita pelo engenheiro Ferri Borges em 1984, com exceção da 30ª lição Manuel Rocha. Eu dizia há pouco que havia uma que não tinha sido, por uma nobre razão. Ela teve lugar no LUNEC, integrada no programa do centenário do nascimento de Manuel Rocha. Com esta exceção, todas as outras lições de Manuel Rocha foram feitas na sala 2 da Fundação Calouste Gulbenkian. Saúdo os presidentes das duas instituições que, de forma continuada, há 38 anos, apoiam, organizam e patrocinam as lições de Manuel Rocha. E uma saudação muito especial para os filhos e genro de Manuel Rocha, a quem me ligam profundos laços de amizade. Os filhos, porque quase os vi nascer, e porque sempre acompanharam a vida profissional e pessoal de seu pai. E o genro, que conheci mais tarde em São Paulo, por quem tenho uma profunda estima. Dear Scott, it was with great pleasure that I have accepted to make your presentation to the audience based on the long friendship we have developed continuously, as I said in Portuguese, during the past 20 years, and the knowledge of your scientific activity as professor and wonderful communicator. We were very pleased with your prompt acceptance of the invitation to deliver this year's Manuel Rocha Memorial Lecture, as well as to write its content, which will be published in the next issue of the journal Soils and Rocks. The brief biography you sent to us will help me to let the audience know some of the more important moments, functions, and activities of your career as geologist and engineering geologist. I believe you agree that it will be most effective if I will make your presentation to the audience in Portuguese. You agree? Ok. O professor Scott Burns obteve os graus de licenciado e de mestre na Universidade de Stanford, na Califórnia, e fez o seu doutoramento na Universidade de Colorado, em Boulder. É membro de mais de 20 organizações profissionais, com relevo para as atividades desenvolvidas pela AEG. A AEG é o acrónimo de Associação de Geologia e Engenharia dos Estados Unidos, na IAEG, International Association of Engineering Geology and Environment, e na GSA, Sociedade Geológica da América. Scott foi eleito presidente da AEG, da Sociedade Americana, Associação Americana, para o período 2002-2003. A eleição é por um ano apenas dessa associação. E foi eleito em Turim presidente da Associação Internacional de Geologia e Engenharia para o período 2014-2018 e, recentemente, em 2019, ele foi eleito membro honorário da mesma Associação Americana, da AEG, Association of Engineering Geology. Scott Burns é professor jubilado de Geologia da Universidade Estadual de Portland, na Califórnia, depois de 32 anos de contínua atividade docente nessa instituição. Contudo, a essa função na Universidade de Portland há a acrescentar intensa atividade docente, exercida também em Lausanne, na Suíça, na Nova Zelândia, bem como nos Estados Unidos e nos estados de Washington, Colorado e Louisiana. Foi supervisor de cerca de 50 teses de mestrado e doutoramento. Especializou a sua atividade em diversas áreas, em especial em Geologia da Engenharia e Ambiental, Geomorfologia, Geologia do Quaternário e Mecânica dos Solos. Em Oregon, tem atuado em diversos projetos de investigação em torno do escorregamento e uso de escorregamentos e uso do solo, estabilidade de taludes, mapeamento de zonas sísmicas, geração de gás radão pelos solos e, muito importante, no tema, que lhe é muito querido, terroir dos vinhos da região, que não é uma palavra que nós usamos muito em Portugal, conhecemos, alguns nem a conhecerão, mas o que isto quer dizer é a relação entre os vinhos, a geologia e o clima. O professor Scott Burns recebeu diversos prémios e distinções em resultado da sua atividade ao longo da carreira, nomeadamente atribuídos por instituições académicas, na maior parte dos casos. É autor de mais de uma centena de publicações científicas e de 2 livros, Environment, Groundwater and Engineering Geology, Applications from Oregon, em 98, e Cataclismos da Colômbia, The Great Missoula Floods, de 2009. Participou como editor e revisor em várias revistas das áreas de Geologia, da Engenharia e do Ambiente, tendo sido responsável pela revisão de mais de uma centena de artigos científicos. No decorrer da sua brilhante carreira, foram-lhe atribuídas várias distinções, desde 1987, parte em reconhecimento da sua prestigiada e animada, quando eu digo animada, porque ele dá animação, atividade docente, e parte em reconhecimento da sua atividade científica e profissional, à qual sempre emprestou um cunho muito pessoal, cheio de preocupações sociais e ambientais. Merecem destaque a distinção que lhe foi concedida pela Divisão de Geologia da Engenharia da tal Sociedade Geológica da América, em 2012, também o prémio Richard Jans, que é talvez o prémio mais importante atual dos Estados Unidos, em Geologia da Engenharia, a título da sua atividade como Top Engineering Geologist in the United States. Em 2011, o prémio Schumacher, pelos serviços públicos prestados às comunidades, também em 2011. E depois, em 2015, o prémio Terzaghi, atribuído pela AEG, mais uma vez, em reconhecimento do seu contributo para o desenvolvimento da geologia nos Estados Unidos, e o prémio Schuster, pela sua investigação na área dos desastres geológicos ocorridos em toda a América do Norte. As suas qualidades de liderança levaram a organizar numerosas visitas de estudo em locais onde ocorreram grandes movimentos terrenos, tais como escorregamentos e desmoronamentos, de maciços terrosos e rochosos, afetando a população atingida por esses fenómenos. E esses fenómenos têm-se vindo, como todos nós sabemos, a agravar em consequência das alterações climáticas que afetam o nosso planeta. Muitas dessas visitas a áreas onde ocorrem grandes movimentos de terreno, que afetaram propriedades e, por vezes, vidas humanas, foram acompanhadas por vários grupos de estudantes e profissionais, bem como jornalistas, permitindo a Scott Burns prestar valiosos serviços à comunidade. Acresce referir que da sua biografia consta ter dado mais de 400 entrevistas a estações de televisão e de rádio, bem como a jornais. Dear Scott, after this short presentation of the main points of your remarkable activity, we are all waiting for having you up in the podium to present your lecture, which I'm sure will contribute to the prestige the Manuel Rocha lecture has all over the world. Thank you.
I am so excited to give this talk today. And first of all, thank you very much to my good friend, Ricardo Oliveira. We have been friends for 30 years. He has been a mentor to me, and also he's a hero. And he has been a leader in our profession all over the world, and it's just a pleasure to be in this town. And then I would also like to dedicate this lecture today to a good friend of ours, Paul Marinos, who I think was a lecturer here before, who recently passed away. He also has been a friend for over 30 years and a mentor to me, and a great human being in rock mechanics and engineering, geology, and soil mechanics, and is a special person in my life. I'm also very excited to come here. Even though I lived in Switzerland for 5 years and taught in Switzerland, I never visited Portugal. This is my last country in Europe to visit. I visited all the little ones, Monaco, San Marino, Liechtenstein, but not here. So I've enjoyed it. What a wonderful country you have got. And I also like wine, and I like port. And so in 2 days, I will be going up north to Porto and enjoying the Douro Valley. I love our profession. Soil mechanics, rock mechanics, engineering, geology, reaching out to people around the world, trying to save lives, save property, everything that we do. And so when I put this talk together, I was thinking about this and relating it back to climate warming, which has been big news, especially the last couple of weeks. And so that's what I'm going to be talking about. This is where I live. This is in Oregon. This is the Columbia Gorge. I'm normally, in a normal year, pre-pandemic, at least once a month there, leading field trips and then doing research there. But as a geologist, wherever I go in the world, I love it because there's always a story. There is always a story of where the rocks came from and what caused this slope and why this river is here and why these mountains are in a straight line. Maybe there's a fault there. And so it's always fun to be able to talk to Mother Nature. Mother Nature is shouting out, saying, this is what's happened. And then you, as a geologist, use those ideas in order to predict the future. Where can we build? Where can we not build? And things like this. Here in the Columbia Gorge, I see these slopes over here. They're all landslides. Don't build there. It's not a good place. There's the heart of an old volcano that is there. On this side, you have many waterfalls. And there's a landslide here, and you can't see another big rock down there that was moved down. So there is a story that is there everywhere we look. So this is the introductory name of the lecture to the real name that is here. So today I'm going to be focusing in on climate warming, and I'll talk about that in a few minutes. And then using the past, geologists study the past in order to help us in the future. And I'm a landslide specialist and rockfall specialist, and I'll be talking about those, but I'm also going to talk about other geological disasters that are out there, very important. So here's my outline. I'm going to talk about little climate change and geodisaster activity, and then I'm going to use case histories. We love case histories because they help us learn what has happened in the past so we don't repeat that in the future. And so I'm going to take you to forest fires because with climate warming, you have many forest fires, and those are big problems that we have got. And I'm going to take you to the Columbia Gorge, which I just showed you there, and a forest fire that I worked on and have predicted for the future. I will mention a little bit about the Appalachian Mountains on the other side of the United States. I'm from the West. This is the East. And they have never been thought of as being a major landslide area, but now they are because of increased hurricanes. And I'll talk a little bit about that. And then an incredible disaster occurred a few years ago in California where you had a combination of fires and then immediately afterwards a big rainstorm, and you had many people killed and many houses destroyed. Montecito. And then I'm going to end up talking about atmospheric river. We never really had this name until just about 20 years ago. And now it is becoming very, very, very common. Why? Because the climate is warming and we are getting more of these atmospheric rivers. And I'm going to talk about one that I was very involved with in 1996. But then I just came from the Pacific Northwest, Oregon, Washington, and British Columbia, and we had a huge atmospheric river that just hit us last week. I was on television 3 times just last week talking about this. So that's what I'm going to be talking about today. Let's see. Okay. So to begin with, climate warming. In the last 2 weeks, we have been talking about COP26 in Glasgow. The whole world has been focusing in on the temperatures that we have got. 1.5 degrees Celsius, that is where we would love to have the temperatures maximally increased to after the original pre-industrial temperatures that we have got. And there were lots of ideas that came out about this. Right now we're at 1.1. But all of these different models, climatic models that we have in the world, they all agree on one thing, that we are going to have many extremes. It's either going to be very, very wet or very, very dry. And with the dry, you're going to have many fires. And it all goes back to water and evaporation from the water in the ocean. The warmer the temperatures, the more water that is evaporated into the air masses, and therefore you have greater rainfall intensity, which causes more landslides and other things like that. And so we'll talk about the wetter and drier things coming up in a second. So when it is wetter and more water in the air masses, you're going to have hurricanes. You're going to have more hurricanes, and you're going to have bigger ones. And we have categories, 1, 2, 3, 4, 5, and we're going to be seeing more of these higher categories. Typhoons in the Indian Ocean and then also in the Pacific Ocean, which are equivalent to hurricanes. Same thing, more and bigger. In the United States, we have tornadoes. It used to be in just one small area in the middle part in a very short period of time for 3 months. Now it is 11 months of the year all the way from Mexico to the Canadian border. More and bigger. And then these atmospheric rivers. And I will explain these coming up. There are going to be more of them and bigger ones that you have coming. And then in India and that part of the world, monsoons, more and bigger. So those are going to be affecting there. Then on the drier end of things, see, those are the 2 extremes. What we're going to be having is more fires. And you've seen, for instance, in Australia, all of the fires that they have had there. In the United States, the western half of the United States has a huge problem right now. And then in my state of Oregon, we have had many, many fires. South America, the same thing. And Africa, and I will mention Madagascar on the next slide. And so all of these places are extremes, and that is coming with the climate warming. Al Jazeera, the English version that just came out last week, listed 6 areas that are the worst hit by climate change in the world today. Madagascar, in Africa, and the drought is just awful. South Sudan, the opposite. Many, many floods, the worst floods in 60 years that are there. In India, they have both. In parts of the country, it's big droughts. The other parts are floods. And people are moving around. They estimated 70% of all of the households in India have moved because of the climate, one way or the other. Bangladesh, they just have flood after flood after flood. 7 major floods in the last 20 years. And then the coral reefs around the world, and we get a lot of seafood that we have. They've figured out 14% of all the coral reefs are destroyed. And if we do not hit that 1.5 degrees Celsius boundary, we will lose many, many more in the future. So, the results of climate warming, more landslides and more debris flows, and I will be talking about those a lot. More flooding. Also, along the coastlines around the world, because the sea level is rising up more and more, we will have more coastal erosion. And then the worst thing, as I mentioned before, is when you have a combination of fire followed by major rainfall events, and I will talk about Montecito. And so, as I mentioned before, also, you have increasing sea temperatures, more hurricanes, typhoons, etc., and then greater rainfall events that we have got. So to begin with, for my first case history, I need to just have a review of forest fires. And so in my state of Oregon, where I'm from, we have many forests, big, big forests, intermediate forests, small ones. Dry forests are found all over California, Nevada, Arizona in the United States, and eastern Oregon. And so they have very, very tiny trees, very dry trees, oak trees, and you have a lot here, juniper trees, and so the forest fires are common. Why? Because it's less than 400 millimeters per year. But then you have intermediate forests. We still have big trees, ponderosa, pine trees in those areas. The average precipitation 400 to 600 millimeters a year in those particular areas. You have more fires, but not as big ones. And then in the wet forests, where I live, where we have Douglas fir and western hemlock, big, beautiful trees, forest fires are very, very rare, even though at the end of the summer it doesn't rain for 2, maybe 3 months. But the yearly rainfall is 1,500 to 2,000 millimeters per year. And so when we have fires, in the dry forest that I mentioned before, you have abundant debris flows afterwards. And you will have rockfall and activation of small landslides. Very similar in the ponderosa types of forests that you have. In the wet forest, though, when you have these forest fires, and they are not very common, what happens is you will have rockfalls and small landslides, but you don't have debris flows. And the reason is the trees are burned on the top, but the roots stay in the ground. And it takes 5 to 10 years for the roots to break down. Once they do, and you have a big atmospheric river come in, then you will mobilize the landslides and you will have debris flows. So there is a time delay that I will talk about in just a second in those types of forests. And so we'll talk a little bit more about that. And then I'm going to be bragging about the U.S. Geological Survey, because they have a team that every time that there is a forest fire in the United States, and now they're doing it in other countries too, they go in immediately. And they do an analysis of the area and what was burned heavily, intermediate, or poorly burned. And then with that, what they will do is predict where the major erosion and the debris flows are going to be afterwards. And they do this primarily in these 2 forests, but they haven't started to work in these areas because there haven't been many fires. I have started, and I'll show you how we have come up with that. So that is the background. Now let's talk about a few case histories. Let me take you to the Columbia Gorge. And maybe some of you have been here. This is the state of Oregon here. This is Washington. This is the Columbia River. We are looking to the east. It is the 4th largest river that we have in North America. And so we had a fire back in 2017. This is a rainforest. It gets over 2.5 meters of rainfall a year in this particular area. So here's a map of my part of the United States. This is Canada, this is Washington, this is Oregon. And so we're talking about this area right here. It is all basalt, one layer on top of another after another, coming out of a hot spot. That hot spot now is over in Idaho, right underneath Yellowstone National Park. And so we have similar geology all up and down the area. And in it, we have the 5th highest waterfall in the United States, Multnomah Falls. There's one lava flow from here to here, one from here to here, one from here to here, one from here to here, and there's a couple more up above. And so that is the area where we head. So we look at a shaded relief map of the area. Here, we're looking north. And so here is the Columbia River moving to the left out to the Pacific Ocean. And then this is the height of the Cascades right here. And I'm going to be showing you this area. That's where the forest fire happened. And so this whole area is what we call a national scenic area. It is not a national park. You can have houses, but anytime you build any business or house in there, it has to pass a commission, has to look good. It doesn't have to stick out because they want the trees and the rocks and the nature to stick out instead. And in our area of the state of Oregon, it's the #1 tourist attraction. And it was created back in 1986. And I apologize, I have everything in acres. And you're all used to hectares, but all you have to do is take my number and divide by 2.47, and you will get your hectares that you have got. But just 2 years ago, 17% of this absolutely beautiful area burned. Wow. And it started in September, so in the fall, and it was started by a high school kid. He was goofing off, and he lit a fire in a field, and then he put it on Facebook. Look what I did. Well, in the end, his family got charged with $15 million bill to help and for the rest of his life, every summer he has to plant trees as a result of this. So the fire started out in the mountains, and you can see the beautiful forest that we have in this particular area here. And so here is a map. So here is the Columbia Gorge. Portland, where I live, is to the left. And it's called the Eagle Creek Fire. And this is what we were seeing for 4 or 5 days. Just the incredible fires everywhere. This is after the fire went out, and you can see areas that were heavily burned and other areas that were not. It bounced around. This is also an area where a lot of people go hiking, and the views from the top of the gorge are incredible. And they eventually, after the fire, they had to close down all of those trails. And so here's the Eagle Creek Fire that you can see in the state of Oregon. I live down in Portland, down here. And so in the end, we almost had 50,000 acres of burning, 17% of this whole area, national scenic area. 7,300 acres highly burned, scorched. There was no A horizon, O horizon left. It was just mineral earth left. And then moderately burned, 80% was still there. And then low ones, and we'll show you in a second. So here you can see this is scorched in this area. These trees are still standing, so that is not very well burned in that particular. And in other areas, not burned at all. But in this particular area here, this is an area that is going to have an incredible erosion once the rains start coming very, very soon. And then again, you can see some areas heavily burned and other areas not burned. So what we did is we went out and we actually flew the whole area, taking air photos, and then digitized it and said, how much of this area is heavily burned, slightly burned, etc. And so here is the gorge right here. And so this particular Oneida Creek Gorge, heavily burned. And then the one right next to it, Horsetail Creek, then Tanner Creek, and then Eagle Creek. Those are the areas that were the worst burned. And so we are now predicting, remember, this is a rainforest, and those roots are still holding the rocks in there. And so it is going to take 5 to 10 years for the roots to break down and the debris flows to come out. And so right afterwards, we had lots of surface erosion, and the creeks were very, very black in color. And then we had increased rockfall on all of the trails, and that was important because we had to close down all of the trails. Engineering geologists had to hike around and see each one of these trails in order to say, is there going to be a potential for rockfall coming down? I'll show you an example what we did in an earlier fire. And then the debris flows, as I mentioned before, when we have an atmospheric river coming in, or what we used to call the Pineapple Express, that will be 5 to 10 years down the road. And so here's a small landslide that occurred right afterwards, but there were not any huge landslides right afterwards, okay? And then I did a lot of television time, and everybody said, what do you predict? And I said, we got to go back to 1991 when we had the last time we had a forest fire here. Everybody said, we had a forest fire in 1991? Yes, but everybody had forgotten about it because remember, high rainfall and the vegetation had grown back and everybody had forgotten about it. And it went right down in back of Multnomah Falls, which I just showed you before. But I said, what happened then will occur in the future. So at Multnomah Falls, where we have many, many tourists come up every year, we now had to put in brood cable fences because rockfall was coming down, and a Japanese tourist was walking up here, and she got hit by a rock, and they closed it down until the brood cable fence was put in that particular area. But now, look at the vegetation has grown back, and so that is what we expect. And then debris flows. And so this area here is this area here. And so to the right, we had one debris flow. I'll show you this coming up in a second. And that's what we call the Royce debris flow. And then this one was a much bigger one, which came right down the center. And I'll show you that one in a second. Now, remember that was 1991. This is 5 years later. This is 1996 when we had these particular debris flows that occurred. Mrs. Royce was making lunch, and she looked out in the pasture in back of her house, and she saw a wall of 2-meter-high boulders rolling across the pasture towards her. And she said to her husband, "Hirsch, I think we better get out of here." The good news is it was moving very slowly, and that was the front of a debris flow coming down, and they survived. And over the next 4 days, their house was completely filled up. And then, in back of where I took this picture, this is what the highway looked like. It was completely slowed down. And so if we went to the left over here, that is where the next debris flow came down. That came down at 10 o'clock at night. And so the highway with all of the trucks was stopped, and they were just lined up here. And then the train, this is a major transportation corridor, was also stopped. 10 o'clock that night, the debris flow came down at a very fast velocity, knocked 6 cars of the train into the river and 9 trucks into the river as a result. And then, if we went back this way, 2001, another 5 years later, we had another debris flow come down and fill up the intersection there, coming out of that area. And so it's this delay reaction. 5 to 10 years later, that's when you get the major debris flows that will be coming down, something that nobody had actually taken a look at. I was very proud after both of these fires because my students, Ryan Cole, Stephen Hay, and Tom Brabish, the last 2 working for the highway department, closed down lanes. You could not have cars next to them until all the slopes were checked by an engineering geologist or rock mechanics person. And then Ryan Cole, all the hiking trails could not be closed. They were closed until they were checked out by an engineering geologist. Some of those trails were closed for a year and a half until they came back. And so the transportation routes and the hiking trails closed until we knew it would be safe for people to go on them. And so for these fires that we have in this type of forest, that is one with a high rainfall event, we know that we will have future debris flows, and we have predicted, and I showed you the 4 that we have there. But it's a delay of 5 to 10 years that is going to be down the road. And actually, we had one from the previous year that killed a lady just this past year. Okay, and so these are where we predicted. So that is we'll go on to the next. So the next one, let me talk a little bit about climate change in the western half of the United States and the wildfires that we have got. And this was a report that just came out just last week. And some of the fires that we had in Southern California that we have there. But I really want to, the poster child, the best example of a major fire followed by a major rainfall event is Montecito, California, January 2018. Dry area of Southern California just outside of Santa Barbara. And so remember it's a dry forest, so very small oaks. And so it burned a very large area. The U.S. Geological Survey came in, mapped the whole area. 2 days later, they had a susceptibility map. This is where the debris flows are going to originate from, and this is where they're going. That report was given to the city of Montecito, but it didn't get applied. And this is a problem, the communication between the scientists and the governmental agencies. And then January 9th, just 1 week later, major storm came into the area. 23 people were killed, 163 injuries, $177 million in damage, $7 million just in emergency response. And a lot of times we forget that it's very expensive to have all the emergency people coming in afterwards. This is what the whole town looked like. All of these debris flows of these large boulders coming down, hitting the houses, destroying the houses, 23 deaths, and then 400 damaged or destroyed houses. And so this is always something that we have to worry about. And that's why the U.S. Geological Survey works on it. Here's their model. They immediately get in and map where all of the burning occurred and the degrees of burning, and we showed you this in the gorge just a few minutes ago. And then, based on that, in their models that they have, they will say this area will produce a debris flow of this size, this area will produce a debris flow of this size, and then if we have different rain. So here they look at the amount, potential rainfall coming in, and then the amount of material moved. And so this is important. This is something to try and save lives and save property. The problem is, in this case, the report came out, but it was not enacted by the government, the local government there. Now we know better about doing this in the future. And then this is the last of all of the examples that I wanted to talk about here, case histories, occurred, in the Pacific Northwest. This atmospheric river. This was a term that we weren't using 2 or 3 years ago. But now, everybody who is a weatherman or weatherwoman on the television and radio is always talking about atmospheric river. And this is just oops, go back to that. This is from my newspaper, in November 17th. So just a very, very short period of time ago that this hit. And this is the area of northern Washington, the next state up. Everything was flooded out, lots of debris flows and landslides created as a result of this. And so in the old days, we used to call these pineapple expresses. Let's see if this is what an atmospheric river is. And they're found all over the world. And they come from the central part of either the Pacific or the Atlantic. And Europe has them too. And so here's Hawaii. And so we call them pineapple expresses because they came from the land of pineapples in Hawaii. And so very, very warm temperatures and loaded with water, and then come in, and here's the Pacific Northwest. There's California, there's Oregon, there's Washington, British Columbia. And this is one from 1996, okay? But the same thing happened this past week. And that's what we were dealing with. And so, as I said, the name atmospheric rivers only originated in the late 1990s. 2 professors at MIT in Boston came up with this idea. And this is a very narrow band of very wet moisture that is coming into an area. And they originate from the middle part of the Pacific and the middle part of the Atlantic. And what they do is they cause lots of landslides, debris flows, and also floods that occur as a result of those. The last major one that hit Europe was in 2015. It was originated in the Caribbean and aimed mostly on the UK, United Kingdom, in that case there. And then something that has just started is now they are going into categories. And they have category 5, 4, 3, 2, 1. Category 5 is the most wet. It's just like they've done for many years with hurricanes. And when you have a category 5 hurricane hitting you, it's a big one. And this has only happened in the last 6 months. And this event that we had, this atmospheric river that hit the Pacific Northwest, was a category 5. And all of us said, wow. And so generally in Oregon, where I live, we get one category 5 one a year. Washington gets one every 2 years. California, Northern California gets one every 3 years. Southern California, one every 10 years. But in California, they need water. And so it's always about 50, when these come in, it's 50% of their annual precipitation that they have. And so I want to take you back to 1996. That was our last major pineapple express or atmospheric river that came and hit our area. And so in 4 days, we had 20 centimeters of rainfall fall in my city. My city has some big mountains and some flat areas. And so I had 3 graduate students who were working with me, and we had lots of flooding, but we also had lots and lots of landslides. And so for the next 2 months, we visited all 712 landslides that we had in our area. And with that, we categorized each landslide. What was the process? What's the geology? What's the soil? What's the slope angle? All of those things, trying to put together a story. Try and figure out, this is an extreme event, where in the town we would get certain types of landslides, other ones in other areas. And so I'm going to show you a few examples. And so a lot of these are going to be urban, but some are going to be also debris flows. For instance, anytime you had a vacant piece of property, who owns that property? Who controls it? We had many landslides on them. And you can see an earth flow that came off of this piece of property, nice house here, I'll show you the other side over here, came down onto the road you see here. And in fact, the next one, where did all that water come from? Well, all of the storm water went down the street, had no place to go. It just went over the edge. There was no collection basin or drain there to pick it up. And you had a major landslide. So what do? You build an I-beam wall, one standard graduate student for size there. But they forgot to put a drain in to collect the water. 2 years later, what happened? The whole thing blew out. And it was exactly this time of the year because it came across the street and hit this lady's house. In the United States, every year we have a special holiday called Thanksgiving. It's coming up this Thursday. And she was having 12 people in for a Thanksgiving meal the next day. She was a little mad at having her house hit there. And so this was, just an example. In the end, this is the only time in my life I've ever actually recommended building a house on an old landslide because you had a huge hole in the ground. They tried to freeze the ground next to it because you had a castle here, and the castle was the walls were falling off and creating huge cracks inside. Freezing the ground did not help. So they built a house over-designed by the geotechnical engineers. But actually, I don't think a very beautiful house in between all these others. But it doesn't matter. It stabilized the slope. They've never had a problem since that time. Let me show you some other examples. A cemetery, very close to us. Where most of the landslides occurred, are the mountains next to Portland. And these are loess soils, wind-blown silt, L-O-E-S-S. For those of you who speak German, Loess is the name. And ML soils, they are highly erodible. And you can see, in English, we would say there is a grave situation in this cemetery that we have here. And so as we would travel around the city of Portland, we would map all of the plastic because it meant that there was a landslide there. This house had to pay over $100,000 to repair and stabilize their land. This one, $70,000. And when we talked to the people here, the lady said, I had a waterfall coming out of my plug gutter for 4 days. All that water concentrated here. And what happened? It failed and you had a landslide. And this is typical in an urban area where you have these types of things happening. But you didn't always have exciting for me, landslides. We had 4 houses in a row that are right here. And what it did is it's the upper part of an old landslide. It was a paleo landslide. If we looked out the window from here, look down the slope, you can see the hummocky topography of an ancient landslide. The whole thing reactivated. And when an old landslide reactivates, it also reactivates at the scarp. And it dropped 1 meter. And it went right through the houses. And so all of those houses had a big crack going right through. All of the pipes, all of the electrical, all broke. And then all of the driveways, etc., all went down. And as a result, those houses were destroyed. They had to be removed as a result. Reactivation of an old landslide, big deal. Here's also reactivation of a landslide. This house was on a slump, and it just rotated like this. This one went right through, new house, only 2 years old. Went right through, the crack went through, the house was destroyed completely as a result of that. And so this is typical with these atmospheric rivers, huge amounts of rainfall in a short period of time. In the end, we had a map of all of the types of landslides we had and processes and where they occurred and where not. And as a result, now we use this in land use planning. And I will end up talking about land use planning in just a few minutes. And I mentioned before, these are the debris flows. We also had them during this period of time too, and we've already talked about those that occurred there. But I didn't talk about these, which was just south of Portland. And you can see here's this one here, there was a house there. And it got hit by a debris flow that came down and killed 4 people in the middle of the night. And the newspaper people said, oh, it's because they cut all of the forest down up above. Well, that may have accelerated things, but the bottom line is they have been having debris flows in this valley for many, many years, thousands of years. It's a process that has been there for a long time, and it happened again. And in this one, in the valley over the mountain that you see here, then you had another debris flow came down and hit this house. The good news is nobody was killed in either of those cases. Here's a smaller debris flow. This house was moved 5 meters off of its base. Not only did it destroy his house, it crushed his car as it bounced down on top of it. And so the good news is many of those landslides were small. And so this is what they would look like beforehand, and then we would come in and we would have a gabion wall. We would put filter fabric down, crushed rock and back, cheap to put in, lasts a long time, well drained, and they have worked for all of those times. So we learned something about these types of landslides that occurred. And in that one event, 52% of all of the landslides occurred in the cut slopes, generally next to roads and next to houses. But then also on the other side, where they had put the fill on the outside of the road, we had 15% of the landslides. And then 9% of them, if they had controlled the water on their property, they would not have had a problem. That is, gutters that are blocked and water is concentrating on the slope, or water coming off of a patio or a driveway or things like that. And why is that a problem? Because landslides are not covered under homeowners insurance. And all of those people, those 9% there, lost everything. They lost their houses, and they would have to pay all of the differences. And that's why we are very involved in the United States in trying to get eventually landslide insurance. We just passed a federal law just this past year, landslides, studying of landslides and gathering of information so then we can actually have insurance. 60 or 30 years ago, 40 years ago, we had no earthquake insurance and no flood insurance. Now we do. And now we need the third other major disaster, and that is going to be landslide insurance. So gathering data so the actuaries can actually put the story together and they can make money. And so the focus during that atmospheric river when it came in, it was all the flooding and the rivers rising up. And the problems there, but in the end, the amount of money that was spent on the landslides was equal to that, and that's something that we forget about as a result of this. And we're seeing more and more of these atmospheric rivers as they occur more and more. So before 1996, there were about an atmospheric river in the Pacific Northwest would occur every 10 to 15 years, one every 10 to 15 years. And then from 1996 until 2010, maybe you would get every couple of years. Now we're getting at least one a year. And this year we've had 2. These huge rainfall events, and it's related back to increased evaporation of water from a warm ocean and the air masses coming into the Northwest. It's interesting, earlier I mentioned about Europe. Actually, there is one that actually hit Iran in 2019. It came off of the Mediterranean area. That's where it originated. And it hit the Zagros Mountains. And 76 people were killed from the landslides and the floods that occurred in that particular one there. Also, we have learned from this that we do not, as geologists and engineers, tell people to look at their water collection systems in their houses. And so when things are designed, when you build a wall, you put weep holes in it, holes that the water will come through and the hydrostatic pressure will not build up and back. But what happens with time? They get clogged with soil. And then what happens is they fall over. so here I've got some of my students with me. The university is only 5 blocks away. We walked over to see this car destroyed here, and right next to it, that car destroyed. And I said, well, we need to spend more time. And every year I spend more and more time getting people to check their houses, make sure that the gutters are working and the water is going into the drains and the drains are actually working. Here is another one of these atmospheric rivers. We had basically 10 centimeters of rainfall in 24 hours. And so a landslide came down and hit this house, and the landslide came out on the side. This was back just in 2009. And so here is the landslide that came down. The next picture will be taken up here. And so you can see the landslide came down and destroyed the house and went out the side. And then the next, let's go down the road. So the normal vegetation around there is this forest. And this is a Douglas fir, western hemlock, good stable forest. But if you go up the hill, right up to here where the landslide occurred, this is what it looked like. And it was obvious to me that all these trees had been cut down. And when you do that, you change the hydrology of the soil. And the landslide came down here. It blocked the road. The water coming down the road hit that landslide, went over the edge, and then caused the landslide that destroyed the house. And so this is an example of cutting too many trees down when they shouldn't have. So the very wealthy man at the top could see the mountains off in the distance, and it caused the landslide. But you had intense rainfall in a short period of time. And in the end, he lost his house. Insurance did not pay it, and he had to have it torn down. Another one of these atmospheric rivers that came in, and that was about 3 years before that. And this was just south of Portland. There was a housing development on the side of a hill. All the houses were on flat pieces of property. Well, we looked at them on the LiDAR. They were all rotational slumps where the landslide had come down and created a flat surface. They didn't realize that they were building all those houses on old landslides. Not a good idea. And so this house was on one of them. That water was diverted, would not pass through that small conduit. And this house, look what happened to that. The whole thing reactivated and was destroyed. And again, they lost everything. Show you another one. These are 2 slumps. This is in the city of Portland. And you have a scarp of the slump, and then a flat surface, and then the toe of the slump. A second one, scarp, flat surface, toe. And what happened was this particular slump reactivated with another atmospheric river in 2002. And so I'm going to show you a picture here where the pipes, when the water pipe and the sewer pipe break, what's it telling you? Mother Nature is shouting out. It is moving. And then the next picture is down here, the parking lot. The next picture will be down here. The next one will be up here with big cracks, and then the last one here. So let's show that. So this was just after Christmas time, January 6, 2006, and the pipelines broke. And people said, whoa, what's happening here? And then they went down to this area right here and look at the parking lot. Oh, we have a little scarp developing. Look at the Christmas trees right after Christmas. And then we go around to the edge, and you have a wee bit of a problem here. The toe of that old landslide has reactivated, and it's moving. And they say, whoa, we better figure out what's going on. So you go up to the top, and you start seeing big cracks. Why? The whole thing is moving in that direction. And then, being a good engineering geologist, what do? You put an inclinometer. You drill a hole down, you put an inclinometer in, and they put it in, and the next day it broke off at 15 meters down. That was the depth of the landslide that had reactivated and was moving. And then eventually what they did is they tore down all of those houses, and those apartment houses, and are not using it. And so these are the things that happens when you get these atmospheric rivers coming in. Another one, this is the same one that house was destroyed that I showed you where they cut the trees down in back. Same night. And this is a stream terrace. And this is the normal vegetation here, but what happened was you had these landslides up here, mainly because there were springs, water coming out of the side of the hill. And this is all a fluvial system, a river system. And the water came down, reactivated the landslide, and it came down. It hit the propane tank, gas tank in back of the house. It caught on fire, and it burned down. The good news is that the people got out of that. The good news also is the house burned down, so fire insurance would pay for it. Whereas if it had not burned down, then they would have gotten no money from the insurance companies. And then the other thing that I teach my students is to read the vegetation. Mother Nature is telling you a story. And so this is the normal vegetation, but look at the vegetation of this whole area up here. It's all deciduous trees. That is alder trees that lose their leaves in the wintertime, whereas these are conifer trees. And after a landslide happens and moves, what happens is you get alder trees coming in. So that was an old landslide. It was a reactivation of an old landslide. We go up here and take another picture. You can see another landslide that occurred up there. They cut the trees down there. Changes the hydrology of the slope, and you had some smaller landslides in those areas. And another big thing that we are very concerned about is reactivation of old landslides. What we have learned is 2/3 of all landslides that occur in Oregon and Washington and British Columbia were old landslides before, and it's just reactivation of those landslides. And a great example occurred just north of Portland. This is where I live, is Kelso, Washington. And in 1998, and this was another smaller atmospheric river that came in. And what happened was, there was many houses here, and the whole area beneath the scarp of an old landslide reactivated, and all the houses were destroyed. And so in the United States history, this is the 4th largest landslide involving houses in U.S. history. 60 houses were destroyed. And I'll show you pictures of these coming up in a second. And then there were 77 houses at the top saying, what are we going to do? Do we sell? Do we move our house, etc.? In the end, if they were far enough from the scarp, it was good. They could have stayed. But most of them sold, got a very low amount of money from the government, so they would get some money. But initially, $6.2 million worth of damage of the infrastructure, streets, pipes, water, sewer, etc., below the scarp, and then $25 million for the houses that were down below. Now, the government came in and said, we'll give you low interest rates. Well, the low interest for those days, 3.5. But here is the scarp that developed. And so here was a small little turnaround here, 4 houses that were right here. Those 4 houses are right here. They're down, they fell in down there. And then you can see one there. All the houses look like this as they reactivated. Nice houses. Here's the major street, and they tried to keep the water and the sewer and the electrical open, but it just did not work. And you can see these houses over here. This guy, Dan, his was the very first house to move. And in fact, his house actually moved down about 250 meters down the hill and did 360 degrees and then fell apart. And so reactivation of these old landslides is a big deal for us, and that's why we go out and map all of the old landslides. Here is a housing development in Portland, and if you go up to the top and you look, there's the scarp. It's moving. They actually have put the plastic in there to keep the water in from going in to reactivate that landslide. We told them, you better do this because otherwise you will have another Kelso in front of you. And just one last example is another reactivation during one of these atmospheric rivers of a housing development. Every year in Portland, they build very expensive houses. They call it the Street of Dreams. And there will be 15 houses, and they build them in the summertime, and then they sell them after people go through them in the fall. And for 1 month, you could go and see all these 15 houses. And so this was called Hidden Lake Estates. So here is just a normal old air photo. Can you see any landslides? No, it's hard to see. But if you do LiDAR, and so this is where the Street of Dreams was over here. But then LiDAR, and I'm sure that most of you know all about LiDAR, you see through the trees. And in our part of the country where trees are everywhere, you want to see the surface. And you can see Mother Nature likes to make flat surfaces, smooth surfaces, no landslides. But you can see here, look there's the scarp of the landslide. There is the landslide. They built the whole housing development on an old landslide. And it started to move. And so I showed you earlier, here is another landslide over here. And that is the one where the 4 houses were split in half back in 1996. And so this is where the old landslide reactivated. And I'll show you the picture of the area. Here is the creek, Abernathy Creek, coming in. And it's coming into a meander bend. It's cutting the erosion into the slope. And so you're looking up, and what's happening, this old landslide is just moving down, including the house that is up on top of it. And you can tell it's got a problem because they put plastic down because they were trying to stop the water going in. And this is the Romeo and Juliet house, $3 million. And so they had a little bit of a problem. And so here is a picture of the Romeo and Juliet house. It was completed in August of that year. This picture I took in February, I think. So just a few months later, they already had to resurface the driveway because it had so many cracks and it had moved so much. And then if we go over and look in the wall here, we can see there's a big crack. And there were 3 major cracks that went through the house as the house was moving down the hill. So in the end, that house had to be torn down. And then the house next to it said, what do we do? There's another very expensive house, $2.9 million. And what we did is we put a cutoff wall in here to stop the water coming down, and then put a buttress at the bottom. And as a result of that, the people got to stay in their house. It's never been a problem. And they could live happily ever after, we hope, until the next major atmospheric river comes in. So let me just take you back to the Appalachian Mountains just for a couple of photos. So all of my pictures have been taken in this part of the United States. Atmospheric rivers coming in here. And then we also have hurricanes that are created in the Caribbean. And then they come into the United States and they move up the coast. And so they hit Georgia, South Carolina, especially North Carolina and Virginia as they are going up. And they create debris flows, landslides. And this is so typical. This is in North Carolina where I have friends that are mapping all of these. And now, because we are having increased hurricanes and increased chances of more landslides, they are now investing money into producing the maps. And what they have found is, studying them in the past, they have had over almost 4,000 known landslides that you have here. 47 people have been killed since 1916, but the numbers are increasing because of the number of landslides that they are in. Big problem in that part of the country. It's equivalent to an atmospheric river, but it is actually different. And then also, this was also just in the news just last week, up in Wales in the United Kingdom. They have where they've been mining coal for a long time. When they take the coal out, they have extra rock and soil, and they put it into a large pile that they call a tip. And some of these tips are very, very steep. And back in 1966, in the town of Aberfan, one of these huge tips created a large landslide that came down and killed 144 people, including 116 children in a grade school. And so they are very sensitive to this, and so they are now mapping all of these tips and restructuring all of them for the potential with the increased atmospheric rivers coming up in the Pacific and hitting the UK and causing similar types of landslides there. So they're working on that. So to conclude, what I want to do is just summarize how we, as geoscientists, as soil mechanics, rock mechanics, engineering geologists, what is our strategy in reducing the number of geodisasters? First of all, we want to communicate too many times we talk to ourselves and we do not talk to other people. We need to talk to governmental agencies, and the information that we generate needs to go into producing better building codes and land use planning. Where do you build and where do you not build? Secondly, we need to communicate our findings to the general public. They need to know more about this. Increase the awareness, get involved in television and blogs and things like this, and radios and newspapers. And then for many of the businesses, produce a resilience plan. What if you have a flood? What if you have an earthquake? What if you have a landslide? How do you keep the doors open that you can continue making money and having jobs in case of that thing happening? So when we work with the governmental agencies, we as the scientists and engineers, infrastructure is the key. We need to change the building codes, and so therefore the infrastructure is preserved. And then land use laws. Where do you build? Where do you not build? We need to do that. And then we need to produce risk maps that tell us where we have the greatest need for investment of money. And then with the public, how do we need to communicate? Preparedness is the key. I live on a subduction zone where we can get earthquakes up to 9 to 10, 9.3. Big ones. And so everybody has a kit in their house and they're prepared. But then we are also working with people on slopes. What happens if your house starts moving? What do you do? And so people need to know what are all of the potential disasters that occur in their area. And then what is the probability of those disasters occurring? And when on the television they say, an atmospheric river is coming here, whoa, you need to be careful in what you're doing. And preparedness at home, you need to have your house prepared for all those things. Our big deal is neighborhoods. Because in case of a natural disaster occurring, your neighbors will be your first responders, or you'll be the first responders to your neighbors. And you need to know who your neighbors are and how you can help them. And as I mentioned, business resilience, get them involved and be prepared for the future. As engineering geologists, I teach my students and have been for many years, you want to make 3 different types of maps that are going to be used by the decision makers. Number 1, inventory maps. Where are these disasters? Where have they occurred in the past? With landslides, you characterize what type of landslide, what's the process, what are the sizes of them. All of those go onto the inventory map. And in the state of Oregon, you get onto the State Geological Survey, and it's called SLIDO, and you can find out every landslide that has occurred in the past. And then from that, now using geographic information systems, GIS, you can put the characteristics of all those slides in, and then the GIS will tell you where also you will have high percentage, medium percentage, low percentage of that landslide occurring, or the flood occurring, or earthquakes, things like that. And that will be very important for your decision makers. And then lastly, risk maps. You combine population and also infrastructure. And if you have a huge landslide problem in the middle of a forest where nobody is living for many, many miles, it's low risk. You don't put your money into that because all government agencies are short of money. And as a result, they only can spend the money on the highest priority places. The risk maps help you do that. And so we need to teach our students how to make all of these things. So in conclusion, engineering geologists, rock mechanics and soil mechanics specialists, all of us need to communicate about these geodisasters. Not only talk among ourselves, but also talk with the public. And more communications with the media, very, very important. And the governments and businesses, and get those businesses to get business resilience plans. And in the past, what do we predict? First of all, we're going to see increased landslides, floods, coastal erosion, just because the climate is warming. More evaporation of seawater is occurring, and that moisture is getting into the atmosphere, and rainfall intensity is increasing, and so will the number of disasters. We need to be proactive. We need to first of all, slow down climate warming. That is going to be a major problem in this world today because we are so split on what to do there. And then not only will we have increased loss of property in the future, and many of it is not insured, but we will also have increased loss of life as a result of this. And so we must respond as a profession. And so thank you very much to all of you for coming out and listening tonight. Thank you.
Thank you, Professor Scott, for your impressive and outstanding lecture. Now I'll switch to Portuguese, if you don't mind. Peço à professora Isabel Fernandes para fazer então os agradecimentos. Obrigado.
Excelentíssimo Senhor Vice-Presidente do UNEC, Eduardo Fortunato, Engenheiro Eduardo Fortunato, ilustres colegas da mesa, ilustre conferencista, professor Scott Burns, excelentíssimos familiares do Sr. Engenheiro Manuel Rocha, que hoje homenageamos mais uma vez, felizmente, e aqui representados pelo seu filho, filha e genro. Meus senhores e minhas senhoras, aceitei com muita satisfação o amável convite da Comissão Científica da Lição Manuel Rocha para fazer o voto de agradecimento ao professor Scott Burns, um reconhecido geólogo de engenharia que desenvolveu a sua atividade como cientista e consultor na área da geotecnia. Now, please allow me to address some words to our distinguished invited speaker in English. Dear Professor Scott Burns, it is a great honor to have you with us today and to learn from you about the important role of engineering geologists in making a better world for the incoming generations. As you stated, scientists need to learn from the past to prevent future disasters. This is part of our DNA, engineering geologists. However, climate changes raise new challenges on a daily basis that we need to anticipate in order to mitigate the increasingly severe effects of flooding, wildfires, and landslides on the communities and on the global economy. The topic you focused on, in the very elegant way you have of expressing yourself, is at the top of the international political and social agenda, as we have seen in the recent meeting in Glasgow and you referred. There is a lively debate about how humankind has contributed and is still contributing to global warming. We individually and collectively have developed quite harmful activities against Mother Nature, which, in your own words, is shouting out. What we heard today is the point of view of a distinguished scientist, professor, and consultant who has developed along the years important activities on the analysis, diagnosis, and remediation of geologic disasters. From your words, we recognize that geologists are well aware of the effect that human activities imprint on nature and how nature usually pays back. The geological disasters and the way they affect the populations were clearly highlighted in your presentation. Besides the scientific and technical remarkable level of your lecture, there is also another aspect that I would like to emphasize, in special to the youngsters that are here today and those that will listen to you in the future. Dear Professor Barnes, you showed today not only the importance of being a notable engineering geologist, but also of being a fantastic communicator. Your incredible dynamism and passion for geology, which is emphasized in your lectures, are clearly reflected in the particular way you have to communicate, not only with the students, but also with the common citizen and the decision makers, as is visible from your TV and radio interviews and your quotes in newspapers. You have the art to turn out complex subjects into simple words based on accurate scientific judgment. Nowadays, this is an essential skill to promote science as an active contributor to the quality of life of humankind and to point out ways for healthy coexistence with nature. The examples you presented are testimonies of your ingenious thinking in the interpretation of quite complex events. Well, thank you for being here with us today, and thank you for sharing with us some of your case histories in which you were involved, and you solved most of them. I now ask the audience to join me to express our appreciation to this excellent lecture with a warm applause.
Muito obrigado, professora Isabel Fernandes, pelas suas palavras. A AEG e a SPG também têm uma medalha e o diploma para entregar ao professor Scott Burns pela sua excelente lição. Professor, please come to the stage. We have here a medal and a diploma to offer you. Bom, aproximamos-nos do fim desta 38ª lição Manuel Rocha e, enfim, faz parte da tradição dar a conhecer o próximo orador. Portanto, a próxima lição será a 39ª, terá lugar, se tudo correr como previsto, também aqui na Fundação Calouste Gulbenkian, no último trimestre do ano 2022, e o orador escolhido pela Comissão Científica para preferir a 39ª lição Manuel Rocha é o ilustre e distinto geotécnico de reconhecido mérito nacional e internacional, o engenheiro investigador principal no Departamento de Barragens de Betão do UNEC, Luís Nolasco Lamas. O tema da 39ª... O tema da 39ª lição Manuel Rocha será anunciado muito oportunamente. Enfim, e passando agora ao encerramento, resta-me, portanto, agradecer em nome da SPG e da AAG a vossa presença nesta importante ocasião para a nossa comunidade geotécnica. Portanto, esta lição foi uma lição inspiradora dos problemas que temos neste momento na nossa sociedade. O que vocês viram nos Estados Unidos também, se calhar a uma escala mais pequena, vamos ter certamente também em Portugal, e não só Portugal continental, como nas nossas ilhas atlânticas. Portanto, um tema atual, proferido com um grande sentido de comunicação, de uma forma muito simples e que nos apraz registar. E, portanto, para terminar, volto a agradecer ao professor Scott Burns, ao Dr. Ricardo Oliveira, que fez as apresentações, à professora Isabel Fernandes, que fez os agradecimentos, à família do engenheiro Manuel Rocha, que mais uma vez fez questão de estar presente e que muito nos honrou com a sua presença, à Fundação Calouste Gulbenkian, na pessoa do Sr. Dr. Guilherme Oliveira Martins, à Associação Geotécnica dos antigos alunos da Universidade Nova de Lisboa, na qualidade do seu presidente, a engenheira Ana Quintela, que está aqui do meu lado direito, e a todos os presentes. Finalizo em nome da AG e da SPG, desejando a todos que daqui a um ano possamos nos voltar a encontrar, e até lá que tenham umas boas festas e um excelente ano de 2022. Muito obrigado pela vossa presença e até breve.